Hi, my name is Hui Ming. I'm here to present our paper, Virtual Reality Racket Sports, Virtual Drills for Exercise and Training. X games require physical output as a way of interaction and engagement with the game, which encourages its use for both exercise and fun. The idea of using X games to improve the health of users have been increasingly promoted by the research and development communities. In addition, X game can also be used as a credible alternative to conventional training. For example, there are multiple previous work exploring X game as a sports training tool, breathing training tool, and to enhance balance, etc. Previous works have explored that the procedural techniques can be efficiently applied, and our method was inspired by previous research and by recent approaches to automate X game level synthesis. Our application extends the current list of such X games by proposing the use of racket sports. There are generally three parts in our paper. So first, we provide a module virtual reality gaming application that can be used to synthesize exercise drills for various racket sports. Here we use table tennis, badminton, mini tennis as examples. Second is for the methodology. Markov chain Monte Carlo optimization method called simulated annealing was used to optimize the exercise drill. Gameplay-related cost terms are defined so that we can manipulate the training objectives and intensity levels to meet user-defined requirements. Third is that we conducted two user studies to evaluate the effectiveness of the application in aspects of exercise and training to show its potential as an exercise and training tool. So here is a general looking of the virtual table tennis X game training environment. As you can see, there is a virtual ball throwing machine was used to generate the shots from the exact same position. And we defined that one exercise drill should consist of a number of shots generated by our system and assembled in a sequential order. HTC table tennis racket and HTC Vive tracker were used to control the virtual racket in the virtual environment. We defined several cost terms to control the generation of the shots. There are two types of cost terms defined in this paper, and their relationship with the total cost term is defined here. The first one is a shot cost term, represented as CS here, contain three sub-cost terms. They are distance, speed, and frequency respectively. The shot cost terms are used to control the exercise drill intensity level, and the WS denotes the weight values of the shot cost terms. The second kind is prior cost term, which is specified before the optimization process, and WP represents the prior cost term values. Let's first look at the shot cost. There are three factors are considered when defining shot cost. More specifically, CS distance denotes the distance covered by the user to complete the drill. It is assumed that the distance between the two adjacent shots, PSI and PSI plus 1, has a positive relationship to the exercise intensity level. If the two adjacent shots are more far away from each other, then it will result in higher exercise intensity. And CS speed denotes the speed of the shots. Also, the moving speed of the shot SI is positively related to the exercise intensity, as the athlete needs to be prepared to quickly decide and adjust his or her movement towards the direction of a moving ball. And CS frequency denotes the frequency with which the shots are generated. The frequency of shot SI is also positively related to exercise intensity, since high frequencies tend to keep an athlete vigilant, and there is no time to rest between adjacent shots. And every single shot SI can be defined as three variables here: the position, the speed, and the frequency. And we also have three prior cost terms considered in this paper. The first is the duration of the drill. It constrains the exercise drill to be of a certain duration. For example, how long the user wants the drill to be, how many shots they want to synthesize in a drill. Next is the variation between the shots. It ensures whether the generated shot will or will not have the same characteristics. When we perform exercise drills that require multiple repetitions of the same shot, the variation between repetitions should be minimized. Finally, the CP side corresponds to the court side. It assigns a side to the synthesized drill. In this case, it would either be a left side or a right side. For all cost terms, A Gaussian model was applied to normalize the values from 0 to 1. Next is optimization. The target objective of the optimization process was to manipulate the exercise intensity. Based on the three components of the shot, position, speed, and frequency, 7 different moves were developed to be chosen by the optimizer. So it's either by change the three terms individually or by change different combinations of the terms. The figure in the right shows how the total cost value changes during the iteration process for the optimization. As we can see here, after about 1,400 iterations, the total cost is gradually decreased to 0, and the optimization process is regarded as finished. Here we have some optimization results showing the variations in exercise drills generated by our training system through keeping the target exercise amounts constant. And we visualized the optimization results in 4 dimensions. During the process, the weights of the shot and prior cost terms remained constant. The first dimension is the numbers close to balls denote the sequence index of the shots. 1 stands for this ball is the first shot, and second stands for the second. 2 stands for second. Here we previously set the exercise drill contains 20 shots as an example. Of course, it could be easily changed in the application. The second dimension is the positions of the balls on the table, are the falling positions of the corresponding shots. The third is that the colors of the balls stand for the speed value of the shot. More red means the speed of the corresponding shot is higher, and more green means lower. Finally, the sizes of the ball represent the frequency of the shot. Larger means the duration between the adjacent shots is shorter. In other words, corresponding shot will be generated faster. We can clearly see here every exercise drill with the same target values do have variations, which can ensure each training drill are not just a repetition of each other. Here we have some other optimization results showing the distribution of shots when varying the target values of the shot cost terms. The visualization dimensions are the same as the previous one, and the weight of the shot and prior cost terms are also remain to be constant. Here we can see clearly that the synthesized X game level do change according to different target values for each shot cost terms. When the target values are relatively smaller, as it shows in the first row of the figures, the shots positions are more close to each other and the speed and frequency of the shots are relatively small compared to the figures in the second row. We can generally divide the levels generated here as low, medium, and high intensity levels. For the first user study, the participant group was comprised of 36 healthy undergraduate and graduate students. A heart rate sensor was used to capture the heart rates of the participants to determine how exercise levels of different difficulty, intensity, and variability affected them. Each participant's mean heart rate was computed after the randomly assigned trial is finished. After the exercise segment of the study, the participants were asked to provide a rating of perceived exertion, RPE, in order to measure the perceived intensity of the exercise drill. A 7-point scale was used. 1 indicated not high at all, and 7 indicated very, very high. Here are the box plots of the obtained results regarding the usage of our developed method as an exercise tool. The ANOVA results indicate our method can be used as an exercise tool. For the second user study, the participant group was comprised of 42 healthy undergraduate and graduate students. 3 examined conditions, no training, virtual reality training, and real-world training were defined and compared to evaluate our application. 2 measurements were captured. The first is the lost shots, which is the number of balls each participant was unable to hit with the table tennis racket. And next is the mistakes. This is the number of balls that were either stopped by the net on the table or bounced outside the table after the player hit the ball. ANOVA was used to compare the performance of our participants, and the results revealed that our method can automatically generate training drills that can help table tennis enthusiasts improve their skills. For more details, please refer to our paper and video. Thanks.